Good day class, welcome to our General Chemistry 2 class. For this video, we are going to cover an overview of chemical kinetics and chemical equilibrium. For the objectives, we will have the following. Number 1, explain the chemical equilibrium in terms of the reaction rates and the reverse reaction. 2, calculate equilibrium constant and the pressure or concentration of reactants and products in an equilibrium mixture. And 3, state Le Chatelier's principle and apply it qualitatively to describe the effect of changes in pressure, concentration, and temperature to a system at equilibrium. So first, let us define chemical kinetics. So chemical kinetics is like stoichiometry. It's a portion of chemistry. Chemical kinetics is the area of chemistry that is concerned with the speed at which a chemical reaction occurs. So basically, it deals with how fast or how slow chemical reactions are taking place. Reaction rate is the measure of how fast a reactant is consumed or how fast a product is formed. This is the measure of the change in concentration of a reactant or a product over time. So concentrations of reactants and products in a chemical reaction, when we talk about reaction rate, is expressed or are expressed in molarity or capital M. And second, for time. So in equation, we have the rate of for reactant. Let's have hypothetical reactant represented by capital A in this equation. So we have change in the concentration of the reactant over the change in time. Negative because since this is consumption, we always expect that the reactant is being used up or being consumed in a chemical reaction. They are the substances that are being consumed in order to produce the expected or desired product. For the product represented by capital B for our product, so rate of reaction rate for the product is represented as delta B, or change in the concentration of the product over change in time. This is positive because product is always being formed. So we expect the concentration to increase, the amount to increase over time. As reactant is being consumed, product is being formed. So it's always negative for the reactant and positive rate for the product. Example, we have 2A reacting as a reactant forming 1B. So we have the reaction rate for the reaction as expressed as -1/2 times change in the concentration of the reactant over change in time. Or for B, it's the same. Okay, let's have this hypothetical chemical reaction, A plus B, or reacting with B to produce C and D with small letters A, B, C, and D representing their stoichiometric coefficients. So for the reaction rate expression for this hypothetical reaction, we shall have -1. All numerators 1 are constant. The denominators are the stoichiometric coefficients in the expression. So we have rate expression for the reaction -1 over A times the change in concentration of A over change in time equals -1 over coefficient of B times delta B, or change in concentration of B over change in time, equals +1 over C times change in concentration of products C over divided by change in concentration of time, equals +1 over coefficient of D times change in concentration of product D divided by change in time. So that's how you express the reaction rate for a particular reaction. Let's have an example. So we have 4 moles of nitrogen dioxide gas reacting with 1 mole of oxygen gas to produce 2 moles of dinitrogen pentaoxide gas. So for the rate reaction expression, we have negative 1 over 4. 4 is the stoichiometric coefficient of the reactant nitrogen dioxide. We multiply negative 1/4 by the change in concentration of nitrogen dioxide over change in time equals negative 1 over 1, or simply none, change in concentration of oxygen over change in time equals positive 1 over 2. 2 is the stoichiometric coefficient of the product, N2O5, or dinitrogen pentaoxide gas, times the change in concentration of the product over change in time. Let's now have the rate constant denoted by small letter k. The rate constant is a constant of proportionality between the reaction rate and the concentrations of the reactants. So expect direct proportion relationship between the reaction rate and the concentrations of the reactants, not of the products. Let's have this simple chemical reaction. So the rate constant for this particular reaction is written as K, or the rate constant, equals the rate of the reaction over the concentration of the reactant. So we multiply the concentrations of the two reactants here for the denominator. So the rate constant is equal to the ratio of rate to the concentrations of the reactant. The rate law is an expression that relates the three: the rate of reaction, the rate constant, and the concentrations of the reactants. In equation, we have rate equals the rate constant times the concentrations of reactants A and B raised to their reaction order. So X and Y are reaction order. So depending on the reaction order as 0 order, 1st order, 2nd order, 3rd order, we raise the concentrations of the reactants to the rate order. Collision theory is the principle behind chemical reactions. According to the theory, a chemical reaction is brought about by collision of reactant molecules or particles, and that the rate of reaction is proportional to the number of collisions. The greater the amount of collision between the molecules, the reactant molecules, over time, the faster is the reaction, or the higher the rate of reaction. Activation energy is the minimum amount of energy that is required to initiate a chemical reaction. So for if you bring together reactants, energy is required to bring about chemical reaction. So that amount of energy required, minimum amount of energy required to initiate a certain chemical reaction, that is called. In this illustration, you will see the reaction progress of letter A, exothermic reaction, and B, endothermic reaction. So you will see the symbol E subscript A representing the activation energy. Notice that in an exothermic reaction, that is reaction represented in the diagram A, we have minimum amount of energy is required to bring about chemical reaction. And in fact, it favors the production of the products C and D. Whereas in B, the representation of the reaction progress of an endothermic reaction, you will see the amount of energy required, minimum amount of energy required, which is the activation energy, is higher than that of the exothermic reaction, and the production of the product CND is less stable as compared to that in the exothermic reaction, meaning the amount of energy must be maintained in order to keep forming the products C and D. So that's how we distinguish between the activation energy between exothermic and endothermic reaction. There are factors that affect the rate of chemical reaction. One is the nature of the reactants. So according to the nature of the reactants, a reaction may proceed at a higher rate or at a slower rate. So again, the rate of reaction is dependent on the amount, the concentration of the reactants, not of the products. Number two is the surface area. Of course, comparing substances that are less exposed in a chemical reaction, there's less collision and therefore less chances for great chemical reaction to take place. So, lower rate of chemical reaction. Concentration of the reactants, of course, increasing concentration of the reactants is increasing the number of particles for collision. Increasing the number of collisions between particles means increase in the rate of chemical reaction. Temperature generally increases rate of chemical reaction because of the collision. The higher the degree of collision between particles, the higher the faster the chemical reaction to take place. Pressure also increases generally chemical reactions. State of matter, it is said to be reactions between or among gaseous are said to be faster than those in solids and in liquids. This is because of the arrangement of molecules. So molecules are more free, have more spaces to move. There are greater degree of collision or amounts of collision, and therefore higher rate of chemical reaction. And of course the bond type. So we studied the different types of chemical bonding, the chemical bonds, and they also differ in strengths. So according to the type of chemical bond, the stronger the chemical bond, the more difficult to break the chemical bond, the higher the energy requirement, so the slower the chemical reaction. The stronger the chemical bond, the type of bond exists between particles, the more difficult to break the particles, and therefore less chances for collision because higher energy is required to bring about the chemical reaction. So bond type is another factor. And catalyst also, but catalyst generally just speeds up chemical reaction. So generally, or in most chemical reactions, these are the common factors that affect the rate of chemical reaction. Okay, let's have here some chemical processes or chemical reactions represented by the following chemical equations. So one is the transformation of liquid water to gaseous water. So this is basically evaporation because it is turning liquid to gas. Physical phase change between liquid and gas. So turning liquid to gas is evaporation. As you can see, the symbol, two arrows, one towards the right and one towards the left. As we know, when water turns gas, it can turn again to liquid water by the reverse process of evaporation that is known as condensation. So initially, water will evaporate and turn to gas. If it is in a closed container, for example, the gaseous water will form water again when temperature becomes slower. So if it is in a closed system, evaporation occurs, condensation as well. And that's the reason why the amount of water is remained or retained because no water molecules are escaping from the system. So there is evaporation and condensation as the two processes occur at same rates, meaning the concentration of the liquid has become equal to the concentration of the gaseous water. That's the time that the process is already at equilibrium. This particular process is considered physical equilibrium because the changes occur are between same changes of the same, different phases of the same substance. So in this case, we have one substance, which is water. That water is changing from one phase to another by evaporation in the forward reaction. And in the backward reaction, it is condensation, that is from gas to liquid. So this one is as an example of a physical equilibrium. The two other examples, calcium carbonate solid, changing to decomposing to calcium oxide solid and carbon dioxide gas in the forward reaction, and in the reverse reaction, the combination of calcium oxide and carbon dioxide to form calcium carbonate. So this is another reaction at equilibrium as indicated by the double arrow, one towards the right and one towards the left, meaning that the decomposition of solid, the rate of the decomposition of solid is the same as the rate of combination of the products to form solid again. So as the two processes, forward and reverse process, occur at same or equal rates, the system is said to be at equilibrium. The other example is ionization. So when the ionization in the forward reaction, in the forward process or reaction is the same as the rate of the reverse or backward process, the system again is said to be at equilibrium. So for these particular examples, we have chemical equilibrium. A chemical equilibrium is a dynamic state in which the rates of the forward and reverse reactions of a reversible reaction or process are equal and the concentrations of the reactants and products no longer change over time. So chemical equilibrium is a state of a chemical reaction wherein the forward reaction occurs at same rate as the backward reaction. So a chemical equilibrium is associated with reversible processes or reactions. That is, the reaction may occur forward and reverse or backward. And when the two reactions, forward and backward or reverse reactions, occur at same rates and the concentrations of the reactants and products are no longer changing, they are already constant, the system, the chemical reaction is said to be at chemical equilibrium. We have two types of chemical equilibrium. We have homogeneous and heterogeneous equilibrium. Homogeneous equilibrium when all reactants and products are in the same phase. Like in this example, we have gaseous hydrogen reacting with gaseous fluorine to produce gaseous hydrogen fluoride. So all the reactants and the product are in gaseous state, and so this reaction is an example of a reaction that is that has an equilibrium, that has a homogeneous equilibrium, that exhibits homogeneous equilibrium. Heterogeneous when reactants and products are not all in the same phase. Like in this example, we have solid zinc carbonate decomposing to solid zinc oxide and gaseous carbon dioxide. So we have a combination of solid and gas, and therefore the reaction is considered a reaction at with or at heterogeneous equilibrium. Speaking of chemical equilibrium, reactions at chemical equilibrium are characterized by what we call equilibrium constant. This quantity is denoted by the following symbols. We have capital K subscript EQ, or capital K subscript C. They all mean the same. They are equilibrium constant. They are a characteristic of reactions that are at equilibrium. Again, that is the rates of the forward and backward or reverse reactions are similar or the same. Chemical equilibrium constant is a value that represents the unchanging concentrations of the reactants and the products in a chemical reaction at equilibrium. So we have established that a chemical equilibrium, that the chemical reaction at the chemical equilibrium is assumed to have concentrations of reactants and products that are no longer changing. So, for example, we have this hypothetical reaction, A plus B, producing C and D with A, B, C small letter, D small letters representing stoichiometric coefficients. So, the equilibrium constant for this particular hypothetical reaction shall be written as capital K for equilibrium constant equals the product of the concentrations of the products. So, in this reaction, we have two products C represented by capital letters C and D. So in the equilibrium constant expression, you write in the numerator the concentrations of the products. So in this reaction, we have products C and D. So their concentrations, and then raise the concentrations by their stoichiometric coefficients. So if in the chemical equation there are coefficients added to balance the equation, then you raise the concentrations of all the substances, reactants, and products in the equation by their respective coefficients or stoichiometric coefficients. So we have C times D concentrations raised to their coefficients over the product of the concentrations of the reactants A and D also raised to their stoichiometric coefficients. So that's how we express the equilibrium constant of a particular reaction at chemical equilibrium or at. Okay, let's have this chemical reaction as an example. To interpret, we have 1 mole of dinitrogen tetraoxide gas producing or changing to 2 moles of nitrogen dioxide gas. So this reaction is assumed to be at equilibrium because of the double arrow between the reactant and the product. So how do we express the equilibrium constant for this particular reaction? So again, the equilibrium constant is expressed as the product of the concentrations of the product raised to their coefficients divided by the concentrations of the reactants also raised to their stoichiometric coefficients. So for this reaction, we shall have the equilibrium constant expression as, so K sub C to represent the equilibrium constant for that reaction. Again, K sub C may also be written as capital K or capital K subscript EQ. So we have the concentration of the product. We only have one product, NO2 or nitrogen dioxide, raised to its coefficient. In the equation, we have a coefficient for the product, which is 2. So we raise the concentration of the product 2 to 2. Divide that by the concentration of the reactant, which in this case is dinitrogen tetraoxide, and it has no coefficient, so we don't need to raise to any coefficient the concentration of the reactant. So this ratio will give us the equilibrium constant for this reaction. This reaction is particularly a homogeneous, is said to be at homogeneous equilibrium because both the reactant and product are of the same phase. So we have mentioned in the previous slide that homogeneous equilibrium is when reactants and products are all in the same phase. So in this example, we have a similar physical states or phases for reactant and product, and therefore the equilibrium is categorized as homogeneous. Since these are gaseous, instead of using concentrations of the reactant and product as an alternative, we shall be using the partial pressures of the reactant and product. So again, especially for homogeneous equilibrium that is composed of reactants and products that are all in the gaseous state, you use the alternative equation, which is just similar in terms of positioning of reactant and product. Only you are computing for the equilibrium constant considering the partial pressures of the reactants and products, not the concentrations of the substances. So to have the alternative equation for the equilibrium constant for this homogeneous equilibrium, we shall have equilibrium constant of this reaction is equal to, or K sub B for this reaction is equal to partial pressure of the product B over partial pressure of the reactant A. So if we are to just convert the concentrations to partial pressures. So we just change the concentrations to partial pressures when the substances involved in the reaction are all gaseous. Can we write the equilibrium constant expression for the following reactions? So for example, number one, we have equilibrium constant expression K equals product first, concentration of HF raised to 2, coefficient 2, over divided by the concentration of hydrogen times the concentration of fluorine. Number 2, we have two products. Product, concentration of the product zinc oxide times the concentration of the other product, carbon dioxide, divided by the concentration of the reactant zinc carbonate. So you practice for the rest of the items later after watching this presentation. Let's have this example. The equilibrium constant partial pressure for the decomposition of phosphorus pentachloride to phosphorus trichloride and molecular chlorine is found to be 1.05 at 250 degrees Celsius. If the equilibrium partial pressures of PCl5 and PCl3 are 0.875 atm and 0.463 atm respectively, what is the equilibrium partial pressure of chlorine gas? The corresponding chemical reaction equation corresponding this reaction involved in our problem is the following. So we have gaseous phosphorus pentachloride decomposing to gaseous phosphorus trichloride and gaseous chlorine. So we first write the expression for the equilibrium constant for the reaction. So that will be K sub B equals equilibrium partial pressure of the products PCl3 and Cl2. So the product of the concentrations or the partial pressure, since the substances are all gaseous, we replace the concentrations with partial pressures. So we have partial pressure of the products PCl3 and PCl5 multiplied, divided by the equilibrium partial pressure of the product, which is PCl5. We are given the partial pressure of the reactant PCl5, which is at 0.875 atm, and PCl3 at 0.463 atm. We are looking for the equilibrium partial pressure of the other reactant, which is chlorine. So to get that, we substitute first all the given. We are given the equilibrium constant 1.05 equals partial pressure of PCl5 is given at 0.463. We are looking for PCl5, so let it be our unknown, divided by the partial pressure of our reactant, which is given at 0.875 atm. Cancel the units. So we shall have the equation, but first let us substitute to get the equation for the equilibrium partial pressure of chlorine. So we will be transposing the denominator 0.875. Okay, so we shall have the substitution of 0.875 to the other side of the equation. So we shall have 1.05 multiplied by 0.875. So we again do transposition. So 0.463 to be divided by the product 1.05 and 0.875. So for the equation, we will be having the equilibrium partial pressure of chlorine gas equals the equilibrium constant of the reaction times the partial pressure of the reactant PCl5 divided by the partial pressure of the product PCl3. So doing the operation, 1.05 times 0.875 divided by 0.463, we shall have 1.98 atm is the equilibrium partial pressure of the other product, chlorine gas. You can do this to practice the equilibrium constant for the reaction. 2 moles of nitrogen dioxide decomposing to 2 moles of nitrogen monoxide and 1 mole of oxygen gas is 1.58 at 1000 Kelvin temperature. Calculate the equilibrium partial pressure of oxygen if the equilibrium partial pressure of nitrogen dioxide is 0.400 atm and the reactant NO or the other reactant NO is 0.270 atm. Let's now try to predict direction of a reaction. So to do this, we need to consider what we call reaction quotient, denoted by Q subscript C. This is obtained by substituting the initial concentrations into the equilibrium constants, because take note that the condition of a reaction to be at equilibrium depends on the initial concentrations of the reactant. So it will determine whether the reaction will be at equilibrium or not. Will it proceed forward, backward, and how can it establish or reach equilibrium? So how do we do this? Let's have this reaction. 1 mole of nitrogen gas reacting with 3 moles of hydrogen gas producing 2 moles of ammonia. So if we are to write its equilibrium constant expression, but since all the substances are in gaseous, instead of using the equation K equals the concentrations of nitrogen ammonia as product divided by the concentration of the reactants hydrogen and nitrogen raised to their exponents, we shall be using the alternative equation for homogeneous reaction. We have equilibrium partial pressures of the product divided by the equilibrium partial pressures of the reactants, also raised by their respective stoichiometric coefficients. So considering the initial concentrations of the reactants and products, we will be computing for the reaction quotient. Reaction quotient is simply substituting the given initial concentration of the product raised to its coefficient. So if we have coefficient, for example, our product ammonia here has coefficient 2. So its initial concentration must be raised to 2. Divide that by the product of the concentrations, initial concentrations of the reactants nitrogen and hydrogen raised to coefficients. Only hydrogen has coefficients, so you need to raise its initial concentration by 3 before you do the division of the concentration of the product by the concentrations of the product. So the symbol subscript zeros are representing or are denoting that the concentrations are initial concentrations. So what is the use of reaction quotient in predicting the direction of a reaction? By comparing the reaction quotient by the equilibrium constant of a reaction. So for example, the reaction quotient is smaller than the equilibrium constant of the reaction, the reaction will favor the formation of the product. So if reaction quotient is less than the okay, if the reaction quotient Q sub C is less than the value of equilibrium constant, then the reaction will favor the formation of the product. So before equilibrium can be established, the reaction will initially favor the formation of the products. When the value of reaction quotient is numerically equal to the value of the equilibrium constant of a reaction, then there is no net change in equilibrium. It will neither favor the formation of reactants or products. But if the reaction quotient is greater than the value of the equilibrium constant of reaction, the reaction will favor the formation of the reactants. So we will be having shift of equilibrium considering the values of the equilibrium constant and reaction quotient. So those are for the quantitative description or prediction of the shift of equilibrium or direction of a reaction. Now we will try to determine the direction of equilibrium or shift of equilibrium considering the Le Chatelier's principle. It states that if an external stress is applied to a system at equilibrium, the system adjusts or shifts in such that the stress is partially offset as it tries to re-establish equilibrium. I wrote here, indicated here, too big, because I need you to imagine water for you to easily predict whether the equilibrium will shift to the left, to the right, or to the side of the product, the side of the reactant, or will the equilibrium remain? Let's imagine water. Sa mga vulcanizing shop, nakakakita kayo ng mga nakatumbang drum, di ba? May tubig yon. So, para dun sa mga kinukulang yung tubig, nag-overheat yung mga sasakyan, so they drop by para maglagay ng tubig. So, water is always available in vulcanizing shops. So, yung tubig sa drum ay at equal level. So, if you are to look at the left and right levels, magkapareho sila. So, we assume that the weight, that the force between the two sides is the same. So, kung ano yung amount of mass, force sa kaliwa, ganun din sa kanan. But if you try to add water, pour water, for example, dito sa side na to, dito na lang sa side na to, sa kanan. Nag-pour kayo ng water sa drum sa side na to. So, yung additional water is not expected to remain in that position as you add it. So, nagdagdag ka dahil may ability yung water to flow. Ang natural tendency niya, according to spontaneity of reaction or process, ay mag-move forward. Addition of water to this side is putting pressure to this side. Water has its mass. Mass is force. So you are putting force. Stress is a kind of force. So you are putting weight, force on this side. And for that stress to be relieved, water has to move forward. So as it moves forward, the shift of equilibrium will be analogous to the flow of water. So, kung mag-add ka dito ng stress because of the additional water, edi you are you are allowing that additional water to flow to the other side in order to maintain the level of water. So this is the stress. To relieve the stress, water has to move forward. So the shift of equilibrium shall be this side. So if it's the reactant side, then the shift of equilibrium will be to the right or to the product side. Same with if you add water to this side, you are putting stress to this side. For the water to maintain equilibrium, water has to move forward. So if it's chemical reaction, you are putting stress here, you're adding concentration, for example, in this side to relieve the stress caused by the addition of that substance, then some has to move forward. So the shift of equilibrium from this side to the other side is what? So if it's product side, then the shift will be towards the left side or reactant side. What about if you remove some water? So kung ito ay water, left and right level ng water, nag-remove ka sa drum halimbawa ng water sa kanan, sa kaliwa, sa kanan. Nag-remove ka ng water. Pag nag-remove ka ng water, hindi naman nangangahulugan na yung water level sa kanan ay mananatili sa kanan. Dahil nagbabawas ka sa isang side, kailangan yung kabilang side ay bumaba rin, mag-move forward. So, ang nangyayari ay, nagbabawas ka dito para ma-maintain, dahil nagpo-flow ang water, para ma-maintain siya, kailangan mag-move. Nagbabawas ka dito, kailangan mag-move naman yung nasa kabilang side para ma-maintain ang equilibrium until such time that you have stopped removing water. So, where is the stress as you remove water from one side? Nandito yung stress kasi mas malaki yung weight dito. Kung saan may malaking weight, nandoon yung stress. At para ma-relieve yung stress, kailangan mag-move forward para ma-maintain yung stress. So, nag-a-adjust yung equilibrium, nag-shift habang nire-re-establish niya yung equilibrium. Okay? So that's the principle, that's the analogy that you can use in order to qualitatively describe the shift or adjustment of equilibrium in reactions at equilibrium. Now, if there are factors that affect the rate of chemical reaction, there are also factors that affect chemical equilibrium. One is concentration. For example, we have this chemical reaction. The effect of concentration can be illustrated using the following. So we have illustrations A, B, and C. So in simple terms, increase in concentration means putting stress on the side of the reactant side. So in this illustration, you see increase in the concentration results to darkening of the solution or of the mixture. So we assume that the concentration in A is less than the concentration is C. So this is what happens as you increase the concentration from A to B to C. So if you are to make use of the Chatellier's principle, adding stress to the reactant side, for example, is putting so if this is your left side of the equation, reactant side, you are putting stress on the left side of the equation. And in order to relieve that stress, equilibrium must shift towards the product side or to the right in order to relieve the stress and to re-establish equilibrium. So the shift of equilibrium as you increase the concentration of the reactant is always towards the right or the product side. On the other hand, if you remove product concentration of the product, so if this is the product, okay, if this is a product, you are getting a product, you are decreasing the concentration of the product, the stress is still on the reactant side. So in order to relieve that stress, some has to move forward. If this is water, water has to move forward to the right side of the equation in order to re-establish the equilibrium. So that's how you use the Le Chatelier's principle in order to predict the shift of equilibrium in terms of concentration. In terms of pressure, you have to consider which side of the equation has greater amount of gas. Increasing pressure in a chemical equation or a chemical reaction at equilibrium is increasing stress or putting stress on that side with higher moles of gas. So between these two, we have 1 mole of hydrogen plus 1 mole of chlorine in the reactant side. Comparing the number of moles of gaseous substances in the reactant and gaseous moles of gaseous products, we have also 2. So the pressure in this case, comparing the moles of reactants and products, we have 2 moles versus 2 moles. So you increase the product is putting stress to neither side. If in case the reactant side has greater number of moles, increasing pressure is putting stress on that side with greater number of moles of gas. So if it's the left side with higher moles of gas, then additional pressure is putting stress on the reactant side. And for the reactant side to relieve the stress, the shift must move forward or towards the right or towards the product side in order to relieve the stress and re-establish equilibrium. If the product has more moles of gas, then increasing pressure is putting stress on the product side. And for the product side to relieve the stress, equilibrium must shift to the left or to the reactant side in order to re-establish the equilibrium. So in terms of pressure, it has something to do with which side has greater moles of gas, and putting addition of pressure, increasing pressure is putting stress on that side. And for that side to relieve the stress is to shift the equilibrium to the opposite direction to re-establish the equilibrium. Another factor is the temperature. So we have here cold versus hot. So the transformation of this gas to another gas, the difference in the color indicates that there is difference in the rate of reaction when you bring about the reaction in different temperatures. Let me give the forward reaction for this reaction. The forward reaction requires heat energy. The backward reaction releases heat energy. So the forward reaction of this reaction is endothermic because it requires absorption of 58 kilojoule per mole to occur or to take place. Increasing temperature means putting stress on the left side. On the left side, reactant side. So if the reaction is endothermic, you expect the heat to be absorbed by the reactant side. So the reactant requires heat. Putting heat or increasing heat means putting stress to the reactant side of the equation. So if this is the reactant side, and this is where heat is present in the equation, then you are putting stress on this side, on the left side, on the reactant side. So for the reactant side, to relieve the stress caused by the increase in temperature, then it has to, equilibrium has to shift forward or towards the product side in order to re-establish equilibrium. But if the reaction is exothermic, you expect heat to be in the product side, and this is negative. So the reverse reaction for this reaction is NO2 plus heat equals reverse nitrogen, N2O4. So if it's the reverse reaction and heat is released by the reaction, the right side has heat in the equation. So if you increase heat, then you are putting stress to the right side. Again, if the reaction is exothermic, you see plus heat in the right side of the chemical equation. So you increase heat is putting stress to the right side. So for the right side to relieve the stress, shift of equilibrium must be towards the left side or the reactant side to reestablish equilibrium. So the effect of temperature depends whether a reaction is exothermic or endothermic. So if you remove stress, if you remove heat, for example, heat in this example is in the right side, left side, reactant side. If you try to remove heat, stress is in the product side. So kung ano yung, kumbaga sa tubig, kung ano yung mas mataas na level, nasa kanya yung stress. Pag nagbawas ka ng heat from the right side, ibig sabihin, sumobra yung tubig sa kabilang side, kailangan niyang magbawas at mag-move forward para ma-re-establish yung equilibrium. So, it's different when you increase heat and remove heat. Removing heat is putting stress to the opposite side. So for that opposite side to relieve the stress, equilibrium must shift towards the opposite side in order to relieve the stress and re-establish equilibrium. And the last factor is catalyst. As I said, catalyst enhances rate of chemical reaction. This is by lowering the activation energy. What is activation energy? Is the minimum energy required to bring about chemical reaction, to initiate a chemical reaction. So catalyst helps lower the energy requirement for a reaction to take place. It also does not alter equilibrium constant nor shift the equilibrium in an equilibrium system. So adding catalyst or additional catalyst in a reaction at equilibrium causes no shift or change in the state of equilibrium of a reaction. But it does help a reaction to reach equilibrium at a faster rate. Mas mabilis ma-reach ng equilibrium ng isang reaction ng equilibrium with the help of a catalyst. Take note that in the initial stage of a reaction, the forward reaction is faster. It will continue until the reverse reaction reaches the same rate as the reverse reaction. So the reaction, a certain chemical reaction, needs time to establish equilibrium. Catalyst helps the reaction to reach equilibrium faster or sooner. We have here illustrations of a catalyst, of a reaction with a catalyst and no catalyst. A is the reaction progress of a reaction with no catalyst. B, with a catalyst. Notice the amount of activation energy in a catalyzed reaction. It is lower. So that is one big help of a catalyst in an equilibrium if we are to establish chemical equilibrium. So can you tell whether the shift of equilibrium is towards the left, the right, or no shift for the following? let's have 1 mole of hydrogen gas reacts with 1 mole of fluorine gas to produce 2 moles of hydrogen fluoride gas. The reaction is exothermic. So you expect plus heat in the right side of the equation because there is release of heat. After the reaction of hydrogen and fluorine, hydrogen fluoride forms but accompanied with release of heat. So HF plus heat in the right side. Let's increase the concentration of hydrogen gas. Increasing the concentration of hydrogen gas is putting stress to the to the reactant side of the equation. So for the reactant side of the equation, to relieve the stress caused by the increase of the concentration of the reactant is to shift the equilibrium towards the right or the product side. So the shift of equilibrium here is to the right, to the product side. Remove product. Let us remove hydrogen fluoride. So removing hydrogen fluoride is, so if this is the product side, you are removing HF, hydrogen fluoride. So if you remove hydrogen fluoride, the stress is on the reactant side, So to re-establish the equilibrium, it has to shift to the right or towards the product side in order to relieve the stress. So removing HF means shift of equilibrium to the right, to the right. Remove HF, remove fluorine gas, remove reactant. Remove reactant is causing stress to the product side. This is the reactant you are removing. The stress is put to the product side. So for the product side, to relieve the stress, shift the equilibrium to the left side of the equation to re-establish equilibrium. Remove heat. Heat is in the right side of the equation. The right side of the equation. Let's remove heat in the right side. So the stress is the higher level of water, if you are to use the analogy of water. The removing heat is putting stress on the left side of the equation. So if it's water that is excess in this side, some has to move forward. So if it's equilibrium, equilibrium must shift to the left in order to re-establish equilibrium. Increasing pressure depending on which side has greater number of moles of gas. So this was given in the earlier slide. They have the same number of moles of gas and therefore no shift of equilibrium. But if in case the right side has more moles of gas, then it will be affected by the increase in pressure, and therefore the shift of equilibrium will be towards the right or product side. For this one, you practice at home. So that concludes our lesson on chemical equilibrium with an overview of chemical kinetics. Thank you for watching. Until next time.